Okay, so in this question, they give us a two-variable function that is defined in this region, and they say that the y partial derivative of this function is bounded, and they also told us that the function f(x0) is continuous at the point 0, 0, and they want us to prove that this function is continuous at the point 0, 0. So first they told us that it's bounded in this region, so basically this is a unit circle, right? And the value of x, y, or the points can only be inside this unit circle. And they also told us that the y partial derivative of this function is bounded. So that basically means that it is smaller than its absolute value is smaller than a positive value m for all x, y inside this domain. And they also told us this, and they want us to prove that it is continuous at the point 0, 0. So to prove, first, how do you prove that a function is continuous at a point? So to prove that a function is continuous at a point, first you must prove that it is, the value of that function at that point has to be defined, right? So f(0, 0) has to be defined. And second, you need to prove that the limit as the point as x, y approach that point of this function has to be equal to that function value at that point. So how do you prove this? Well, you can use the definition of limits. So the definition of limits, it's the same thing from just one variable function. So there exists an epsilon. Epsilon is written this way. Yes, greater than 0, and then there exists a delta greater than 0, where, so for a two variable, x has to be where when x, the absolute value of x is smaller than that delta, absolute value of y is smaller than that delta, then the value of the function has the distance between the value of the function and that limit, or in this case we want it to approach this point, right? So it's f(0, 0) has to be smaller than epsilon. So we just have to show that this is the case, then this limit exists. So if we can prove these two things are true, then that means that this function is continuous at the point 0, 0. So now we're gonna go with the proof. So first, we're gonna prove. Change the color. Never mind. Okay. So first we're gonna prove. So we're gonna write proof. So first, we're gonna use the first condition they gave us, is that the y partial derivative of this function is bounded. So fy of xy is bounded. That means there exists a positive value m, where the absolute value of this y partial derivative of fxy has to be smaller than or equal to m for all xy belonging to the domain. That's what we have. And now we're going to use the Lagrange theorem, or the intermediate values theorem. So the Lagrange theorem for a one variable function is that there exists a c that is in between a and b, in between the open interval a and b, such that the derivative of fx at x equal to c at x equal to c is equal to fb minus f of a over a b minus a. So this is the change in y, this is the change in x. For a two variable function, it is the same. So here we're taking the partial derivative, the y partial derivative. So we're gonna keep x there. Here is c, and then here's the change in. I will let z equal to this function. So here is the change in this z. So it's just x b f x a over But this is basically b minus a. This is the change in y. So it's a change of z, over the change of y. If it's y partial derivative, if it's x partial derivative, then it would be the change in x here, and this is still the change in z. So it's the same thing. So we're gonna use I will just call it the intermediate value theorem. Yeah, I'm not sure what it's called. Maybe it's still called the Lagrange theorem. So according to this, that means that so we're gonna look at when in this interval, so 0 to y. So here, so basically there's gonna be why is it? So basically we have f y of x c fy of x c or c, I'm not sure how to call it, is equal to f of x y minus f of x 0 over, so y minus 0, so it's just y, right? And then I'm gonna write it this way: f of x y minus f of x 0 is equal to y f y x c. And now I'm gonna take the absolute value of both sides. So it's equal to this absolute value and this one. Now we know that this whatever y is, it has to be smaller than or equal to m. Then we get this whole thing is smaller than or equal to y m. The absolute value of y m. Sometimes I forget to say the absolute value, but anyway. So next is okay. You can move it. So next is, now we have this. Now we're gonna use the next condition that they give us, is that fx, the function fx0. So basically this is a function of only one variable of x, because we have fixed y equal to 0, is continuous at the point 0, 0. So since it is continuous at that point, what that means is that, well, I'll just say, since fx0 is continuous at 0, 0, that means that the limit of when x approaches 0 of fx0 has to be equal to 0, 0. And what does that mean? That means that oh, I forgot one thing. Let me just, I forgot. Okay, I'll just copy this, move it down for now. I forgot one thing. So first, I will just say for all epsilon greater than 0, let delta 1 equal to epsilon over 2m. Then when y is the absolute value of y is in between is smaller than delta 1, then we will get this. So this is just something that we just assume. It has to be smaller than it has to be smaller than, so here we just replace this with this, so it's gonna be, how much is it? Smaller than this. Yeah, and this one is just equal to epsilon over 2. So basically this whole thing is smaller than epsilon over 2. And now we use the other condition that we just wrote. So since this is continuous at the point 0, 0, that means that this limit is true. Then we use the definition of limits. So we already have this epsilon, for all epsilon greater than 0 that we gave. So we just so that means that here there exists a delta 2 that is greater than 0. that when x is in between this delta 2, the absolute value of x is smaller than this delta 2, then f of x0 minus f of 0, 0, the absolute value of it has to be smaller than epsilon, epsilon be smaller than epsilon over 2. Here you can put it, you can also put it epsilon, but I will put it epsilon over 2. It's the same thing. It implies the same thing. It doesn't matter if it's epsilon multiplied by 1,000, because epsilon is for all number. Oh wait, I wrote epsilon wrong in this one. Yeah, epsilon is for all number greater than 0. So epsilon can be as small as it wants, as long as it's still greater than 0. So you can put epsilon over 2. It doesn't change anything, but you will see why we do it. So now we have these two conditions, right? We have the first one. This one actually is not the one that we're gonna use. We're gonna use this one. Sorry. What? Yeah. Okay. So yeah, we're gonna use these two conditions. So here, now we can prove this. So we have f of x y minus f of x0, absolute value of it. So yeah, we're using which one? Yeah, we're trying to prove that this is the case here for all epsilon greater than 0, right? So this one we can write it as fxy minus f of f of x0, and then we plus it back, so it stays the same here. Minus f of 0, 0 is equal to this, and now we're going to use the inequality of absolute values. We know that this has to be smaller than or equal to this, right? Yes, so this is the inequality, just making sure. So yeah, this one has to be smaller than this, so this whole thing has to be smaller than or equal to this. Yeah, and now we have this one, so this is equal to, well, it's not equal to, it's smaller than this thing, smaller than epsilon over 2. Oh sorry, that's a timer. And then we just, so this one is smaller than this, and this one is smaller than epsilon over 2 also, and this is just equal to epsilon. So, and this is all related to this epsilon greater than or equal to 0. Wait, I forgot one thing again. A bit of proving. Sorry, I forgot to give. Yeah, sometimes these proofs are, they forget some stuff. So here we have to let delta, where delta is equal to the minimum of delta E or delta R. Oh wait, I accidentally speak Chinese. So let delta is equal to the minimum of delta 1 and delta 2. So yeah, one of them, and because this thing we let what here y smaller than delta 1, y smaller than delta 2. If we just take a smaller value of the 2 and just use that delta instead, it will still be the same. You can think about it, try to think about it yourself, it will still be the same. So we let delta is the minimum of one of them, and then we say when x is smaller than this delta and y is smaller than this delta, I mean the absolute value of x and the absolute value of y is smaller than this delta, then so we get this, then we get this, and then we have proven that this is smaller than epsilon. So meaning that for all epsilon greater than 0, there exists a delta. There's the minimum of these two, which is greater than 0 also. It's greater than 0. Yes, it's all greater than 0 also, because again m here is greater than 0, this is greater than 0, so this one is greater than 0. I'm just making sure in these proofs. So exists a delta greater than 0. What? Greater than 0 when x is smaller than this delta, the absolute value of x is smaller than this delta, the absolute value of y is smaller than this delta. Then we get f of xy minus f of 0, 0 is smaller than epsilon, thus proven that this limit does indeed exist. And it's equal to f of 0, 0. Yeah. And if you're questioning if f00 exists or not, it does exist, because the point 0, 0 is inside of this domain, right? So it's here, it's inside of this domain. So f of 0, 0 is defined. So I guess I didn't write that from the start, but it is defined. So we have this limit exists, and also f of 0, 0 is defined. That means that the function fx is continuous at point 0, 0. Yes, that is the proof. Oh, sorry. That is the proof. Sorry if this proof was a bit of a mess, or this video was a bit of a mess, but yeah, that is the proof. So thank you for watching.